Hello everyone, welcome to the session. So now in this video, we will talk about the types of linear regression. Okay, so I hope that until so far you already have, learned about the mathematical intuition of linear regression that we have covered up so far, right? I have talked about the equation of a straight line in while explaining the mathematical intuition, which is y is equals to mx plus c. And if you remember, we have taken one example of demonstrating that given a height, what will be the optimal weight of a person, or vice versa. Anything can be the case, right? Now, whenever we are talking about the types of linear regression, depending upon how many independent features we do have majorly three different types of linear regression, which we will going to talk about in today's session. So the very first type, which I think with the help of that example only, I have completely explained you the mathematical intuition, which is a simple linear regression. The concept of simple linear regression. So what is the meaning of this? When I'm saying simple linear regression, the simple meaning is that here we will be having only one independent feature. Okay. So the equation will looks like y is equals to mx plus c, where this is the equation of a best fit line, right? Y cap, which we want to make a prediction, right? For example, given this kind of a graph, what we want to do, given a data points, we want to create a best fit line, right? Let's say ki on the x-axis, we want to have, let's say in a given data, we will be having a height of a person. And on the basis of the given height, what will be the optimal weight of that particular person? That is the idea. It can be vice versa, but let's consider this case. And we have given a lot many data points, right? Correspond to that data points, we have tried to demonstrate this line. So here if we will be able to observe, we will be having only one x. We will be having only one x, which is height. And this is y, which we want to predict. So this is the y cap, the line which demonstrates a best fit line, which is equals to mx plus c, where this c is as of now seems to be 0. C is nothing but is the intercept, and m is nothing but is the slope of a line, right? This is an example of a simple linear regression. All the mathematical part, I think I have tried to explain with the help of this example only, with the help of this single independent feature only, right? Here this x is the independent feature that we have. Independent feature that we have. But do you think in real world scenario, we have only single feature? No, it's not like that. It's very rare that this kind of scenario will happen. That's where we will be having second type, which is called as a multiple linear regression. So what is the literal meaning of this? Simply, in a simple layman words, if I'll try to explain to you, if you will be having a multiple features, and that is something which you will see in the real-time use cases, right? We do have multiple independent features rather than we will be having a single feature. So when we will be having a multiple features, x1, x2, x3, x4, and so on, in that scenario, you will call the same linear regression algorithm as multiple linear regression algorithm. So what is the meaning of this? Where we will be having a multiple independent features. Multiple independent features. Make sense? So this is something that you will call it as a multiple linear regression. For example, in the upcoming sessions, you will observe that at the very end of a linear regression part, I am trying to show you one complete end-to-end project of a house price prediction. And there you will observe that in order to do the prediction of a house, we will be having multiple features. Obviously, whenever we're talking about a price of a house, it depends on multiple things, right? What is the area, locality of that house? How much is the, volume of that house? Or in which locality it belongs? How many number of bedrooms we have? Is it 2 BHK, 3 BHK, 4 BHK, and so on? So whether metro is nearby or not, whether the local market is nearby or not, and depending upon all these factors, the rates will be determined of any particular flat or a house, right? So that is a very best example of a multiple linear regression, which we will do practically also in the upcoming sessions. So house price prediction is a very apt example of multiple linear regression. So in terms of implementation wise, everything will remain same, The only thing which you will observe will get changed is that here you will be having a value of x1, x2, x3, x4. So your equation of best fit line will get changed to y is equals to m1 x1 plus m2 x2 plus m3 x3 plus m4 x4. Let's say you will be having 4 features plus c. So intercept will be 1, but now you will be having 4 coefficients. Let's say while doing the prediction of a house, you will be having 4 features, x1, x2, x3 and x4. And finally you will be having a value of y, which is a target value, right? It's a target value, which is the price of a house. And this x1, x2, x3, x4 indicates the independent features. And obviously, while doing a prediction of a house, we do have multiple independent features. That is for sure. So what is happening? We will be having 4 features, and corresponding to those 4 features, we are trying to, let's assume, predict the house price. Okay. So in this case, your equation will get changed from that simple one to this multiple one, where this m1, m2, m3, m4, now you will be having all these 4 slopes. Okay. And this value of c is again, it will always be 1. It is intercept, right? That is the only difference in terms of the equation, mathematical intuition. Everything will remain same. The only thing is that here you will be having a multiple features, here you will be having a single feature. That's why it is called as simple linear regression, and the another one is called as multiple linear regression. I hope it makes sense. I have given you the example also for the same. Both of them examples are also, I hope, pretty much clear to everyone, right? Let's move to the last type of a linear regression, which we called as a polynomial linear regression. So whenever we are talking about this kind of linear regression, see, when we are talking about the above case, anyhow, we are dealing with a linear based data. Have you observed the equation, both of the equations, whether this is equation number 1, this equation number 1, or whether this equation number 2, can I say both of these equations belongs to a straight line? So both of these things are valid only if we will be having a linear data where the relationship between the dependent and independent feature is linear in nature, right? So can I say in both these cases, we will be having we should have, that is the preliminary condition, that this linear regression, whether it's a simple one or a multiple linear regression, deals only with a linear based data. Linear data. Can I say everyone? Linear data between, or linear relationship you can say. That is also you can say linear relationship between dependent and independent feature, right? Dependent and independent feature. If I'll ask you what is the meaning of independent and dependent feature, I hope everyone knows. For example, in this case, x, which is the height, is the independent feature, and this weight is dependent feature, which is dependent on what value of height we have, right? So this is the important property which you can note. Here the important concept which we have to understand is that what if we will be having a non-linear based relationship? It might be the case that we will be having some kind of a data in which a linear line is not possible, right? For example, I will show you within few minutes also. For example, you will be having some data. Let's say there exists a data which is having a level. For example, if you will be able to observe in companies, what happened is that we have a level 1, level 2, level 3, level 4 and so on. If you will go to Google company, Amazon, they are having a levels of positions, right? And depending upon how much higher level you have, you will be having a higher salary. Let's say corresponding to level, we will be having a salary or a package. Now, what is happening is, let's assume that the data, this is kind of a relationship it holds. The data belongs to like this, maybe here, 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 here. You can draw a straight line, but when you draw a straight line, it might be the case that you will be having a maximum error in that scenario. Means, what is happening here, that level and the salary might hold a polynomial relationship. So basically, this is a non-linear based relationship that we have. In that case, whenever we want or we are aware that our data holds a non-linear based relationship, not a linear one. If we will try to create a linear line, it is having a maximum error. In order to avoid that, we will go for a non-linear based line, which is again an example of a polynomial based linear regression. If I will be having a non-linear relationship between the dependent and independent features, that is level and the salary, at that point of time we will go for a polynomial linear regression. I hope it is clear now. So what is happening in this case, your equation will look like here. If you will be able to observe, this is x, right? And on the basis of this x, we will be having the value of y. So your equation will be same. Y cap is equals to m. Now it depends on the degree. For example, m1 x1. Okay, it will remain same only. m1 x, then m1, for example, x square, m1 x cube plus c. So what is happening here? I am saying that maximum degree is equal to 3. In that case, this kind of equation will form. For example, if you will say that the degree is equal to 2, means maximum degree is 2, then your equation will look like m1 x plus m2 x square. This is not m1, it will be m2 m3 and so on. So similarly here also what will happen? Here if you will be able to observe, we will be having a equation where we will be having a degree of maximum as 2, right? This is what we will be having. So in this way you can have a degree of 1, 2, 3, 4 and so on. That's why it's called as polynomial regression, right? So this is the example of a polynomial regression where we will be having only single feature, which is a level, but it is non-linearly having a non-linear relationship between the dependent and the independent features. For example, if I'll just show you now this example also, here if you will be able to observe, what we have done is we have imported the libraries. Just want to show you the simple thing. That's why I have taken this example. Let's say I will be, let me just connect it down. So let me do one more thing in the meanwhile it is connecting. I will upload a data set. I'll show you what this data is all about. So now here if you will be able to observe, let me just import the files first of all, the packages which is required. Once this is done, we will try to load the data, income dataset.csv. Now what I have done is, I have just try to show you the polynomial regression, okay? That's why what I have done is I have tried to separate my independent and dependent features. So x is something which is a independent features. So before showing this also, let me do one thing. Let me show you the data set, what it is all about. Let's first of all load it. So we will load the CSV file with the help of this read_CSV function. After that, if you will be able to see, the data set is all about position, level and salary. As I told you that as the level increases, person salary also increases. So here if you will be able to observe, level 1 is having salary of 45,000, level 2 is having salary of 50,000, level 3 60,000 and so on. I hope you can see a pattern also. Now what I have done is, I have taken indexes, all the rows, and I am taking a column starting from 1 because I don't care what is the position. If I will be having a level, I can easily interpret the salary also. So I'll try to just let down the last column because that is the final target value which I will try to put down in the y value. Okay? So this is what I have done. So if I just want to show you what is x all about, let me just show you. And what is y all about? You can see x contains the levels and y contains the corresponding salaries of a person. And you will observe that as the level increases from 1 to 10, salary, the number is also increasing, right? After that, what we can do is, if we'll try to, train a simple linear regression model. So what will happen? You can call simple linear regression and you can fit that on the value of x and y. Your model will be ready. But let's say you want to fit a polynomial regression. So what will happen? First of all, you need to import this polynomial features and define the degree so that it will get to know which kind of polynomial regression you want to implement. For example, here I am saying that degree is 2. So it will make an equation of that maximum degree as x square. Okay. And then we will fit that model into the fit_transform. So what will happen is the complete x value will now get transformed as per that equation. And then we can apply that same linear regression on that new x value. So if I just try to show you what this x_poly will look like, you will see now it contains not a single level value, it contains 3 values here, right? X square. So we will be having 3 values corresponding to all the 10 data points that we have, right? 1, 1, 1, 1, 2, 4, 1, 3, 9. If you will be able to see, we will be having 1, then 1 and then square of that. X and then x square, x and then x square until the last value. I hope it is clear to everyone. Now, if you will be able to visualize the two charts, which gives you more clarity, just try to understand the concept here that this is a kind of a pattern or the data points that we have. Can you see this? Level is there, salary is there. And if you will be able to see, if I try to plot a straight line here, it is making a lot of errors. Can you see? I hope you all know what is the meaning of error. The actual data, which is red line, red dot, and the predicted one, which is available in the violet line, right? Or you can say blue line. So this is the error. And you can observe that this error is very much huge for all the levels that we have. But if I try to draw the same thing in the polynomial regression, I somehow able to reduce that error because the kind of curve is now it is showing as a polynomial curve, right? So this is the overall idea behind the polynomial regression, where what we try to do is whenever our graph or whenever our data holds a non-linear relationship, that's where we will go for the polynomial linear regression concept, right? I hope it makes sense. This is the overall idea behind the types of linear regression.